lecture we are going to discuss some examples about a very important topic in physics, which is collisions and scattering. So, we are going to look at a few examples as an application of the momentum and energy principle and the Newton's laws of motion that we have discussed in the earlier weeks. So, first let us start about collisions in daily life, that is at the scale of our human experience. So, when the word collision comes to our mind, usually so the things that comes to our mind is like a cricket ball hitting a bat or a tennis ball hitting a tennis racket, such as in this case, or some let us say this boy which is jumping on this skateboard. So, these are examples where kind of collisions are useful, and sometimes collisions are also can be very bad, such as collision between two persons or collision between two cars, etc. But we all have experience with collisions, and it is very common in our daily life, and sometimes collision is good for us, sometimes it is bad for us, but this is something that we should know how to analyze. So, we are going to take some examples from daily life. So, our first example is a jumping on a skateboard. So, it is described in this picture. So, there is a boy. So, the skateboard was initially standing still, that is stationary on the road, and there is some sort of a stair. The boy was standing here and he was running on this upper surface, and then he jumped on the skateboard. So, he jumped on the skateboard, like this is the trajectory of the center of mass of the boy, and as a result what will happen? So, the skateboard will try to move. So, it will get a jerk impact, and as a result of this impact the skateboard will try to move to the right with the boy. So, this is how he initiates the skateboard. So, this is the example. So, there are some details. So, the mass of the boy is 40 kg and the mass of the skateboard is 5 kg. Now, he jumps with a speed of 5 meter per second, and it's the moment when he lands on the skateboard, the direction of his motion was 30 degree with the horizontal bending downwards. The impact with the skateboard has a time duration of 0.05 second. So, it is a very small, almost like a 50 millisecond small. The question is that determine the final speed v along the horizontal surface by which is of the skateboard, and the total normal force N exerted by the surface on the skateboard wheels during the impact. So, how do we analyze this kind of problem? So, let us go step by step. So, first let us define our system. So, this is, as you remember, the first step in our modeling. So, we are going to take the boy plus the skateboard as our system, and we will look at the everything else in the surrounding, and then we will look at the interactions. So, boy plus the skateboard, this is our system, and then everything else in the surrounding. So, what are the so this is our system. So, what else are there in the surrounding? So, they have mass. So, earth is interacting with them. So, there is this earth's gravity. Then the road, so the skateboard is placed on the road. So, the road will provide a force on the skateboard. So, there is this normal force. Now, note that we are going to consider the system for only during the duration of the collision. So, the skateboard has just gained the velocity from 0 to v, but it has not moved really. So, this is our assumption. So, then within that condition we are going to ignore any friction. is ignored. So, this is the situation. So, this is one important thing that you should keep in mind, that before just directly plugging into formula, you should set up in this way the what are the system, what are the interactions, so that you can get the right intuition about solving the problem and understand the motion. Now, in addition, there are two other forces which are internal forces in the system. So, the buoy, due to jump, it creates a, the buoy collides with the skateboard and it creates a, so the buoy hits the skateboard at an angle 30 degree with the horizontal. So, it has a downward velocity Vy and a, let us call it Vb, B for the buoy, the Vb x component. Now, because of this horizontal component, so there is a downward momentum with which the buoy is hitting the skateboard, and the buoy after the impact, the buoy is and the skateboard are moving in the horizontally towards right. So, only in the x direction. So, that means the y direction, the downward momentum of the buoy was stopped by the skateboard. So, the buoy is hitting the skateboard with some force and the skateboard is also hitting the buoy with some force by Newton's third law of motion. So, there is a change in the momentum. So, this is the internal force between the buoy and the skateboard. So, this is the setup. So, now, but the point is that all these forces are kind of a priori not known. So, in this case, the useful way to analyze is by looking at the change in momentum of the system. So, let us write it down. So, at the beginning of the interval, so the interval is delta t is equal to 0.05 second, and then at the end of the interval. So, this is the interval during which of impact duration. So, at the beginning, what was the momentum of the buoy? So, the buoy's momentum was its mass. So, let us say in the x direction. So, this is our x axis and this is our positive y axis. So, the buoy's momentum was mv time x. All the momentums by velocities are by the way with respect to the ground. What about the momentum of the skateboard? The skateboard was initially at rest, so its momentum was 0. At the end of the interval, the buoy and skateboard are moving together. So, they have a, so let us say mb equal to mass of buoy, which is 40 kg, and ms is mass of skateboard, which is 5 kg. Now, our momentum principle. Now, the point is, given this situation and this assumption, there is no external force in the horizontal direction. So, there is a conservation of the x component of the momentum. So, the fact we can write it by equating them. So, this will immediately give the V as mb times now, given this picture, the x component of the initial velocity was 15 meter per second. So, the x component is 15 meter per second into cos 30 degree. So, the x component was, so x component was 5 meter per second. So, the v is given by this particular expression. So, now you can, so we can plug in the numbers, we get 40 by 45 into 5 cos 30 is root 3 by 2 meter per second. So, this is the answer to the first part. Now, to answer the second part of the question asks that what is the total normal force N exerted by the surface on the skateboard. For that, let us look at the what happens in the y component. So, again the y component at the beginning of the momentum of the interval, the momentum of the boy in the y direction is mv times mvy. Skateboard was stationary. So, this was 0. At the end of the interval, there is no y component, no momentum of the mass or boy of the skateboard into y direction. So, this is 0. Now, note that we cannot equate them because there are forces in the external direction. So, we have to remember our principle that the change in momentum in a time interval delta t is equal to the net force acting on a system, and this is our system. So, what are the forces? So, the force, there are two forces, one force by the road and the other force is gravity, which is by the earth. As we have discussed many times that these two forces are very different forces, they have different physical origin. So, in this case our change in the momentum is 0 minus so this is final minus initial, and this must be equal to. So, we are going to take, this is our positive x direction, this is our positive y direction. So, we are going to take in the positive x direction. So, then the n is positive and the weight is negative. Times delta t. Now, this gives us the n. So, n is given by now let us plug in the numbers. So, this is 40 plus 5 into, I am going to assume that g is 10 meter per second square. So, this is kg, kg comes from here, meter per second square, which is Newton, and then the boy's mass is 40 into the speed is, so vby. So, remember that the boy is coming, so this is vby, which by our which must be negative. So, this is 40 times 5 meter per second into sine 30 degree with a minus sign divided by duration of the collision, which is 0.045 second, and this is 40 kg. So, I will let you do the simplification and to show that this answer is about 2450 Newton. Now, note one thing, that sometimes we often say that during a collision the forces due to impact are so large that you can ignore the other forces that are continuous. In this case, this weight is a continuous force that is acting continuously, and this part is the impact or impulsive force due to the collision. But note that if you compare the magnitude of these two forces, then the impulsive force is large, but not too large compared to the weight. So, you cannot ignore weight in this case. So, this is how we analyze this sort of problems. So, let us take another example of collision from daily life. So, this is a striking a tennis ball. So, here is a tennis player and there is a ball which was dropped. So, this is the trajectory of the ball shown in the orange. So, it hit the ground and then was on the rise, and then she hits the ball and returns it. So, when the ball hit the racket, this V1 is the velocity of the ball and it is in the direction shown by this green arrow. So, that it basically makes an angle 10 degree with the horizontal, and then the return after the ball hits the racket, it changes its velocity and now it is moving in this direction with a velocity V2. Now, there are more details. So, V1, the speed magnitude of V1 is 15 meter per second, and after impact, after it get hit by the racket, the speed increased to 22 meter per second. The mass of the ball is 60 gram and the duration of contact with the rocket, that is the duration of impulse, is 0.05 second. So, the question is, what is the average force R exerted by the racket on the ball? So, with what force she hits the ball? Also, find the angle B with the R. So, not only the magnitude of the force, also find the direction of the force. So, this is the question. Again, as before, we first start by defining our system. In this case, it is simplest to consider the tennis ball as our system, because the problem asks about what are the force acts on the tennis ball. So, this is our system. So, then the racket is in the surrounding. So, in the surrounding, so what are the forces acting on this tennis ball? So, the one force is its weight, which is by the due to the earth. So, these are the interactions, and the other force in some direction is by the racket. So, this force is kind of an impulsive force due to collision, and this is a continuous force. So, now our goal is to analyze the problem. Again, we will, so the simplest, we will follow the approach that we will look at the time interval delta t, during which, so the delta t, the impact time interval, so at the beginning of this time interval, and we will look at the momentum of the system at the end of this time interval. So, it is given in this picture that this is the V1 and it makes an angle 10 degree. Now, we define as by, so these are the positive directions of x and y axis. So, the ball, the momentum of the ball was V1 and then let us say x, and at the end of the time interval the momentum of the ball is V2. So, it goes with a angle 20 degree. So, if we look at the x direction, so what happens, the x component came towards left, gets hit and then moves towards switches, reverses and goes to the right with a bigger magnitude. Then if we look at the difference, this difference must be equal to the external forces acting on the system. Now, in this case the only external force in the horizontal direction. So, the gravity does not have a component in the horizontal direction. So, the only external force must be due to the racket. So, this equation, let us call it equation 1, will give us the x component of the force R. Similarly, for the y direction, so for the y direction, the if we look at the y direction of the velocity, it was going like this, and after the collision, so y component, it was rising, the ball was rising. So, the y component of the velocity is in the positive direction. After the collision, the ball is still rising. So, look at the picture. So, after the collision, the ball is still rising with a different speed in the y component. So, ball is still rising. There is a difference. So, there is a change in momentum in the y direction as well. So, before the collision, at the beginning of the time interval, the momentum in the y direction is this much, and at the end of the time interval, the momentum is this. So, then the change in momentum is and then by applying our energy momentum principle, the change in the momentum of the system must be due to the external force acting on the system times the duration of the interval. So, there are now two external forces. One is Ry, which is acting in the upward direction. The other is the weight of the ball, which is acting in the downward direction. So, Ry, according to our sign convention, Ry is positive and the weight is negative times the time interval. So, then from this equation we can rearrange the terms to get the Ry will be the change in momentum divided by collision duration times mvg. Okay. So, now I see I made a mistake. So, in the x direction, so this is the force. So, our rule is multiplied by delta t. So, the change in the x component of the momentum should be the Rx times delta t. So, then from here we can write Rx to be mb to x minus v1 x divided by delta t. So, let us now write down the values. So, v1 x is equal to 15 meter per second times. So, this is in the negative direction. So, this must be cos 10 degree. v1 y is in the positive direction. So, this is 15 meter per second into sin 10 degree. v2 y from this picture, v2 x is in the positive direction. So, this is 22 meter per second in and v2 y, which is also in the positive direction. So, this is 22 meter per second, sorry. So, this must be cos, and the y component has sin. Now, given this MB is equal to how much is MB? This is 60 gram. So, this is 0.06 kg and delta T as I mentioned is 0.05 centimeter second, and let us assume that G is equal to 9.81 meter per second square. So, then I invite you to plug in these numbers and compute what is Rx and Ry. Now, once you get this, so the second part of the problem asks that what is the direction of Rx and Ry. So, here in this case how do I get the direction? So, this is Rx, this is Ry. So, then the by vector law of addition the resultant of this is the actual force acting in this direction and this is the angle B. Now, one thing that so from once we compute Rx and Ry, we can get the magnitude which is R as simply from the components, and then we can get, and remember from this picture it is clear that Rx is R times cos of B and Ry is R times sin of B, and from this picture it is clear that Rx would be in this direction, that is both Rx and Ry are positive according components are positive according to our sign convention. Now, here one thing I want to mention that in this situation it is clear that B is a angle in the first quadrant, but in general we do not know what is the B. So, it can be in any quadrant. So, this is a generic problem in computation. So, you have determined the components and now you want to find out the direction. So, in this case you always get two solutions, because if you have an angle, so if you have an angle like this as acute angle like this, so there are this angle will also have the same cosine components with different sine components. So, in general if you have a trigonometric equation of this form, so this cos B is equal to Rx by R, that means B is equal to cos inverse Rx by R, and sin B is equal to Ry by R, that means B is equal to sin inverse Ry by R. So, it is always safe to compute B as an inverse of both cos and the sin and then determine. So, then you get an unique answer, because when you check both of them, the usually textbook what they mention is to calculate tan of B, which is Ry by Rx, which means B is equal to tan inverse of Ry by Rx. So, this I would not recommend, because in this has an ambiguity, because there are two angles with the same tangent by as you know from the trigonometric property of angles. So, it is better to look at the simultaneous solution of inverse cos and inverse sin to determine the angle. So, after this our next example will be something that is not so familiar from our everyday life, but now we are going to go toward smaller length scales. Even at smaller length scales, the collisions play a very significant role. So, that is going to be our next example. Thank you.